Hi everyone, my name is Tiffany, and today I'm going to talk about two sorting algorithms, topological sort and heap sort. So the main topics we're going to cover today are directed acyclic graph, topological sort, heap, and heap sort. A directed acyclic graph is a directed graph with no cycles, and it is also called a DAG. So a DAG can be flattened, which is very important for topological sorting. Flattened means that you can arrange a DAG in a way that all the edges are in the same direction. And we will see a flattened DAG in the next slide. So here you can see three graphs. The first one is not a DAG because it is not even directed. And the second one is a DAG because it is directed and it has no cycles. And the third one is not a DAG because you can see there is a cycle here. Here in this image below, you can see that we have a DAG, and then there are two topological ordering to flatten the DAG. So in this way, you can just arrange all the nodes in one line, and then at the same time, all the edges can point to the same direction. Usually we refer it as pointing forward. And there's an important note that the topological arrangement of a graph is not necessarily unique. So let's see the formal definition of topological ordering. A topological ordering of a graph G is an ordering of its nodes as V1, V2 till Vn, so that for every edge between every node, we have I smaller than j, or in other words, all the edges point forward in the ordering. And there are two important theorems. The first one is that if a directed graph G has topological ordering, then G is a DAG. And the second one is that if a directed graph G is a DAG, then G has topological ordering. The two theorems can be proved by contradiction, but we're not gonna do it here today. And then let's see what is topological sort. First, we need to introduce the fact that in every DAG G, there is a node V with no incoming edges. And we're gonna use this important fact to carry on with our topological sort. So the algorithm for topological sorting is that we can first find a node V with no incoming edges and order it first. And then we delete this node V from the graph. Then we recursively compute a topological ordering of the graph without the node V, and then append this order after V. So what this means is that here in this graph, first we can see node V1 is a node without incoming edges. So we delete V1 from the graph, and then V1 will be the first node in our topological ordering of this graph. Then after we delete V1, we find that V2 is also a node without any incoming edges. So here in figure C, you can see that V2 is deleted. And then we can see that V3, V4, and V5, and finally until V6, all the nodes can be deleted one by one and then append to the topological ordering of the same graph. And then the arrangement we can produce by this algorithm is just the topological ordering of the original graph G. The time complexity of topological sort is V plus E. It is the sum of the amount of nodes and edges, because in this algorithm, you need to traverse all of the nodes and edges to first make sure that you can find a node with no incoming edges. And second, you also need to take notes of them when you delete them from the graph. And there is an important application for topological sort. We can use it for DAG testing. So when you are given a directed graph, you can use a topological sort to test if there is a cycle here within the graph. So if it is not a DAG, then you can definitely find that there is, at some point of sorting, you can find no nodes with no incoming edges. But if it is a DAG, then you can definitely use the algorithm to traverse until the very last node of the graph. We have two example problems in Leetcode, number 207 and number 210. So in problem number 207 about course schedule, you're given a number of courses and their prerequisites, and you need to determine if you can finish all the courses. So in other words, this means that you need to check the dependencies of all the courses and figure out if there exists any mutual dependencies, which means the courses are prerequisites of each other at the same time. And this can be done by first construct a dependency graph of all the courses, and then run topological sorting to check if this graph is a DAG. So if there is a cycle within the dependencies, it means that at some point there must be a mutual dependency and you cannot finish all the courses. But if it is a DAG, then it means that there are no cycles in the dependencies and you can finish all the courses. So for problem number 210, what you need to do is not only making the decision of whether you can finish all the courses or not, but also return and ordering of the courses you need to take. And then let's talk about heap sort. So first, let's talk about the data structure called heap. Heap stores n elements in a complete binary tree, which is also called CBT. So usually there are two categories of heaps, max heap or min heap. In max heap, every node's value is greater than or equal to its children, and the greatest value in the heap is at the root of the tree. And then in min heap, it's completely the opposite. So you can have the smallest value of all in the root node. Usually we use data structures like array to implement a heap. Where given a node with index I, you can quickly find its left child and right child just by multiplying the index I by 2 and then add either 1 or 2. And then let's see the basic operations for heap and the time complexities. Usually in heap operations, you have a helper function called heapify, which means maintain the ordering of the elements in the heap. And the time complexity for heapifying is log n. So when you push an element to heap, you can just directly add a new element you want to push to the very end of the array and then heapify. So after heapifying the heap, you can get a correctly arranged heap. And when you want to pop the largest or the smallest element of the heap, you can just return what is currently at the root of the tree, and then remove it from the array, and then just heapify. And in Heapsort, when you are given n elements, the first thing you do is pushing all the elements to a heap. And this takes n times log n, because pushing one element to the heap takes log n. And then after you construct the heap, you pop all the elements from the heap. And the order that the elements are popped off from the heap is just the ordering you require. So the overall complexity is O and log n. And for Heapsort, we also have two examples. So in the first problem, the first thing you can do is counting the frequency of all the integers, and then sorting the integers by the frequencies. And here you can use heap sort, and all you need to do is saving the k most frequent elements. You can either use max heap or min heap in this problem. And in question 659, it is kind of similar to the former one, but it is a little bit more complicated. In question number 659, it is kind of similar to the first one because you also need to deal with the frequencies of different values. And similarly, you can use the heap to deal with the ordering of them. That is all for topological sort and heap sort. And thank you for listening.